So welcome to our HPC panel. HPC is an exciting field where scientists and engineers use raw computational horsepower to solve some of the biggest challenges in the world today, from weather prediction to making engines, aircraft engines, more fuel efficient and much more besides. So today what we're going to do is to discuss RISC-V and HPC and see what kind of potential, the huge potential that it could have, the impact that it could have, and how we're going to get there. So welcome to my panel. Thank you very much for coming. Can I ask each of you to introduce yourself and tell us how you would define HPC and what you and your organization are broadly doing in the field?
All right. So my name is Patricia Gonzalez Guerrero. I'm a research scientist at Lawrence Berkeley National Laboratory in the Applied Math and Computer Research Division. So what we care in our group is about how high performance is going to look in the following years. And we are using RISC-V to do a lot of our explorations, our research explorations, and evaluations of architecture.
So hello, my name's Nick. I'm from EPCC all the way up in Scotland in Edinburgh. I suppose I've got feet in two camps. So firstly in the HPC side of things, I've done a lot of work on weather modelling. For instance, I developed one of the main weather models used by the UK Met Office. And also I lead quite a large component of the UK Exascale software programme. But my research interests are what technologies we're going to have in the next 5 to 10 years in supercomputing. And again, RISC-V is a big potential thing here. And I chair the HPC SIG in RISC-V with those interests.
Travis.
Hi, I'm Travis Lanier. I'm the Chief Product Officer at Ventana. I define HPC as solving large, complex problem using thousands of processors combined together efficiently. We're working with various HPC programs out there to create customized RISC-V solutions.
Wei-Han.
Yeah, my name is Wei-Han, so I'm the architecture lead in Tenstorrent. So I lead a high-performance CPU design team. I also lead a chiplet architecture team, define the next generation Tenstorrent AI solution with the heterogeneity in there. Yeah, so we're interested in the RISC-V just because it's a very open architecture, and then we can do a lot of things with it. So flexibility and open. Yeah.
Thank you very much. Okay, so welcome everybody. First question, what makes high-performance computing such an interesting field to work in, especially for RISC-V? And what makes it unique in terms of compute requirements? Nick, can we start with you?
Well, I think the reason it's interesting is pretty much every scientific discovery in the last 20-odd years has required simulation to some extent. So it really is core to the advances of society. And it's fascinating to see all the different bits and pieces, and I think it really pushes the requirements of the architecture to be moving up to that level of performance and the compute side and the memory side and bring it all together on that.
Great. Travis, what do you reckon?
Yeah, well, what I like about it is it seems to be a field that's almost perfectly defined for RISC-V. So you start off with that common base. You have the RISC-V architecture for your basic fundamental computations, and the secret sauce in HPC is actually the vector unit. And so what you do is you have that common base and you allow people to differentiate with that large vector unit. And so we're seeing a lot of traction and interest in that capability in HPC.
Patricia, what do you think?
So I agree with Nick that scientific discovery and solving the pressing issues of today's societies requires high performance computing. And today, I'm going to be a little bit dramatic here, saying that high-performance computing is a little bit in crisis because what we saw is that we expected an increase from one generation to the next generation of high-performance computing to deliver 1,000 times more performance, right? That's not happening anymore. When you see the trends, there is no way to extract more performance of these machines. So this is quite an interesting or quite an exciting time to reinvent HPC to be able to deliver the performance that we need to solve these scientific problems and these scientific dilemmas.
Wei-Han.
Yeah, so HPC is kind of my passion when I was studying in the graduate school. But the real reason I working in Tenstorrent, I started investigating this is I do see there's a conversion of HPC technology to the AI technology. They actually are solving same kind of problem, right? They need massive amount of compute, they need a lot of memory bandwidth, they need very high speed, low latency network. So I draw that analogy. So HPC hasn't been in the field for 40 years and 60 years study maybe, right? But I want to learn from that technology and how to move that into the AI computation. So that's why I'm very interested in this area.
Thanks very much. Well, maybe you can expand on that. Our next question is, why is HPC such an interesting architecture for developing new generations of HPC, and how will the high-performance computing challenge affect what we're doing with the ISA? How does it challenge the ISA and our community?
To be honest, I've been working on 4 different ISA, right? So my career has been x86, and then I went to a startup called PSMI working on PowerPC. I joined Apple and then working on ARM. This is my number 4 ISA I've been working on in my career on the CPU design. I don't see there too much semantic difference, right, to be honest. To be honest, I think the HPC technology is really pushing on the boundary on the implementation on memory technology, networking technology, microarchitecture, right? So if you say that, do I have to have RISC-V to build a high-performance computing? I don't think so. And I also don't want to aggressively push in a specific feature to RISC-V architecture. I want to keep it clean, right? And then do whatever they do better, right? But HPC has an acceleration, right? I don't want to put in too many garbage or even the baggage to the RISC-V architecture. So my focus on here is basically applying the RISC-V architecture, building a very strong microarchitecture and system architecture, and do whatever they want. There's a geopolitical reason that people now are converging to RISC-V technology because it's an open standard, right? So government, if they want to have sustained investment, they want the open technology. Like you see the license problem with the Qualcomm to the ARM, right? That exemplifies the problem of the closed ecosystem. So all the government, if they want to invest on this sustainable technology, they have to go to open standard. I think RISC-V is riding that wave. To be honest, I don't see there's a particular reason you have to be RISC-V, but this open standard actually very good for the long-term investment from government or in a corporate perspective. Yeah.
Thank you. Nick, from an academic point of view, what's your thoughts?
Well, I actually want to pick up a point that Wei-Han made before. I think maybe we need to redefine what we mean by high-performance computing, because we've got AI, ML, and we say high-performance computing, and I'm the worst offender here. Sort of actually what we mean is scientific computing. And I think high-performance computing is the thing that sits below them and enables all of them. And actually, traditionally we've talked about supercomputers, but actually, in reality, we probably want to have a wider thing there. We've heard a lot about automotive, for instance, and we need lots of performance there as well. So a lot of the underlying requirements and concepts, I think, are far more shared than maybe first looking at HPC naturally silos it a bit more. And this is really key because we're seeing a lot of work going on in the AI ML space, and we also want to share that in the scientific computing space. So, I mean, your technology, the Tenstorrent cards are a prime example of that, but also things like the matrix extensions. There's so many benefits we can have more widely across high-performance computing, whether it's AI ML or scientific computing, and we need to make sure that we really are sharing them properly and connecting these different things together. So that's something I've been thinking for a while. Actually, we need to be a little bit careful how we're using some of this phrasing and terminology. And on the openness side of things, what was quite interesting is we run a lot of workshops and events at supercomputing conferences. And we had a Mentimeter thing up at ISC, the big European conference, and people were voting what's most important or exciting about RISC-V to you in the HPC community. And what won was the openness. And that really shocked me because I didn't think the HPC community would really care that much. I thought other things they might be more interested in, but it came out top and top by quite a long way. So clearly some of the messaging we've been doing has been landing, but also clearly people see why it's important and beneficial there.
Yeah, so I'll latch on to something you said there where you mentioned you have high performance, you have HPC, then you have AI. And they have some common elements as far as high performance processing. One, you're seeing lots and lots of processors being hooked together. So how do you hook these things all together? Then you're also seeing some commonality in the workloads now. We were talking backstage before this, but even in HPC, they're starting to see AI may be able to do some of these traditional engineering type of computations is effectively doing that. So what we're seeing with some of our HPC partners is they're actually wanting to make their processing flexible enough to both do traditional scientific compute, but maybe do some more AI type of operations in there. And so that's when we have this platform, we're looking at this concept of, it's not just the CPU, but how do you hook these many processors together efficiently inside of a platform to accelerate all these things running at the same time? How do you keep that memory fed? And then how do you have a tool chain or a compiler tool chain that allows you to put the customizations on top of that?
Patricia, any thoughts from you?
So I think to add up to that, to what Travis just said, is like what is key in HPC is that you have you don't have one or two or three, or you have we're talking about thousands of cores. We're talking about 10,000 cores working in parallel to solve the same problem. We're talking about a system that is going to run for 2 weeks, and what is more important is that like, in spite of the complexity on how powerful these machines are, they are not necessarily delivering today what we need to solve the scientific problems. So I think another important aspect to all this is to look into specialization. So how can we connect specialized pieces of hardware that can accelerate particular scientific kernels? And that's something that can be enabled by the openness of RISC-V, because it enables the flexibility to evaluate different options. And like with the variety of scientific applications that we have, we're going to have kind of a variety of accelerators at the same time that can connect to these HPC systems. So I think that's also quite important.
Thank you. Can I also ask, kind of following on from that, is there anything you think any other things you think that RISC-V will enable the HPC community to do that it previously couldn't do, that it was, restricted from doing with other architectures?
So in our group, for example, we were working into quantum computing control, for example, and then someone developed their own little accelerator to be able to meet the critical timing, right? And what happened is that the accelerator did the job. I mean, the processor that they designed for this particular application, quantum computing control, was very nice, did their job, but when we try to scale up or try to disseminate for people to program it, we kind of hit a block. And then that's something that the RISC-V enabled us, the RISC-V architecture enabled us to solve. So when we adopted a RISC-V processor to do this control, we could have the specialization that we needed, because quantum control is very particular, but at the same time we enabled a wide variety of users to program this and to write C code for this and play and experiment with this. So I think, so it's quite powerful.
Anybody else have thoughts? What else could RISC-V enable HPC to do that it couldn't before? Yeah?
So it's interesting, this is actually something we talked about in the HPC SIG last week, because we were talking about RISC-V adoption, and Jeff made the point, it's not enough to be sort of comparable, we have to actually enable something new. What personally really excites me is the number of RISC-V accelerators that are out or are coming out. Things like the Thunderbird from Inspire Semi, that'll be out soon. Things like the Tenstorrent cards. And the fact is you've got a lot more flexibility around memory and loading in memory. And a lot of our workloads are, to some extent, memory bound. And actually, potentially, what this enables us to do is to specialize, and I completely agree with what you're saying on the specialization, for these sorts of things. So, let me load some data in, concurrently let me compute, concurrently let me write it out, and I can do it in a way that suits the application. And maybe that's then a lot stronger than just having an existing solution where the designers have set that for you. So I think this value add and this specialization is crucial here. And in my opinion, we're seeing this in some of these accelerator cards, and it's super exciting from that perspective.
Travis?
Yeah, I'll just build upon what he said about the specialized accelerators. I think what you have with RISC-V, it goes back to my earlier comment, is you have that common base. And what we're seeing is before, if you wanted to do a supercomputer, a lot of times you're either using a processor, which is off the shelf, or maybe you went and begged them to put a little bit of customization in there for you, or you had to do a clean sheet design from the ground up, hundreds of millions, if not $1 billion design to go and do that. And with RISC-V, you can start with some of these designs, and you can have a base CPU, and you can just focus on doing what you want to do different in your vector unit. Since, as I said earlier, that's generally where they're excited about in the HPC space, at least from the processor portion of it.
Yeah.
And then how do you feed all these things together? So it's a much lower threshold to get something much more adapted to your specialized computing.
Okay, great.
So I feel the openness of the RISC-V standard is actually bring the diversity of the architecture supporting the high-performance compute. If you look on x86, right, or ARM, they come in serving a particular market, like they serving the server market, cloud market, or PC market. So in general, their microarchitecture is designed for that specific reason. So it's sometimes you're suited for high-performance computing. Right? So what RISC-V does is that it gives you this wide space of innovation you can have, and then with that diversity of the architecture, eventually enable you to run the application differently. And also like co-design, like Tenstorrent has using RISC-V for our AI accelerator, is a simple RISC-V processor that dispatches the instruction closely coupled with the accelerator. Each processor is doing special function. We also designed the general purpose high performance computing, like AMD Zen 4, Zen 5 grade processor. So this diversity actually enable the application optimized for particular area using our diversity of the architecture. That's the reason why I think this is important. Like the people say here, the past architecture is designed for server, for PC, but sometimes it's not great for high performance computing. Yeah, this opens up a new domain of the application, even software, hardware co-design.
Thank you. And Wei-Han, I'd like to pick up on something you were saying earlier was about you didn't want things to get too complex in terms of extensions. I mean, what we were discussing maybe backstage is what kind of existing extensions will be key to HPC and what do you think we need to develop? I mean, Travis, you were saying vector is the key thing that they're interested.
So I want to draw this analogy, like I work in Apple for like 13 years, right? So Apple has like, Cindy processor closely coupled with the ARM processor, right? So they have Cindy, then they later invented metric multiplication engine, right? Close coupled to the core, but multiple cores share that. They have Apple Neural Engine, right? That using for, high performance compute, high power, high efficient, computational AI inference. Then they have GPU. So there are all this different layer of the computation capability to solve one AI problem. So you can see that some application like, some AI inference is very short, tightly coupled with the application. They can use in the Apple Matrix engine. And more complex, where they can go to Apple Neural Engine, and even more complex using GPU. So I think the possibility of RISC-V is that they can using all this diversity of different layer of the application in terms of its power efficiency performance to fully optimize the HPC stack. And that's where I see that this is actually going. And we actually utilize this technology that way. I'm not keen interested in adding acceleration extension to RISC-V ISA today. Because I think with the layer of the acceleration you dispatch, you can actually closely differentiate what application you're using to what kind of application performance and power efficiency you want to achieve. But I don't want to add too much baggage on RISC-V ISA. I say, okay, because now AI is hot, it's adding an AI ISA extension. Metric multiplication engine, right? Very simple one is sufficient. Yeah.
Thank you. I mean, Patricia, Nick, from the more research side, what are your thoughts on extensions and what we need?
So I think the future of high-performance computing is in heterogeneity and specialization. So I think an ISA extension that enables CPU cores to communicate with accelerators, or with within a system that is completely heterogeneous, where I have different types of processors working together, where I have all these, maybe a GEM accelerator, maybe a fast Fourier transform accelerator. So this ISA extension that enables the communication of all these systems in a low latency way is going to be key for this to succeed. Right now, what we have is we have this, this HPC is based on cache coherency, like the communication is basically a coherent scheme. So when we make the accelerators participate on this cache coherence mechanism, you're adding hundreds of clock cycles in latency. So that's why I think an ISA extension that would enable that in a general way, like agreeing with what you just said, like you don't want anything that is too specific that only works for one thing, but something that enables this variety of heterogeneity and specialization would be really, really cool to have. I don't know what I don't know if you agree.
I completely agree, and I think the composable extensions task group led by Jan Gray, sort of looking at tightly coupled accelerators is a very interesting and important sort of activity that's going on, because potentially it enables, or it's the magic, if you like, that enables at least the first step of this. So yeah, absolutely.
Yeah.
Okay.
Yeah, well, you're saying words that are music to my ears. I mean, tightly coupled acceleration is part of what we do, right? So this actually goes beyond HPC. So this is actually RISC-V in general, what you bring to the table. And you see it in HPC, you see it in data centers. How do you tightly couple in this acceleration? Because in the end, you're hitting the wall on what you can do inside of these processors. And so you're going to have these accelerators to continue to get the performance from that. And so that's why we're focusing on having a platform that allows you to tightly couple these things in there from a low latency perspective to do the specific workloads, because there's going to be a lot of different types of workloads.
Great, thank you. So I wouldn't be doing my job if I didn't mention AI. We touched on it a little bit already, but who has some interesting things to say about that?
Yeah, so we talked about AI earlier, and we were seeing some of the convergence between that. Again, we said some of the things that are traditional engineering compute can actually be replaced by AI computation. I think I may have touched on similarly, we saw some of these HPC initiatives where they're saying, look, it seems to be such a wave, we want to make our HPC accelerator able to do some AI-ish type things. Maybe it's not going to be a pure AI accelerator, but they're going to add the AI capability to that. So again, we're making sure that these things can be easily integrated to the processor. I think we're definitely in favor of standardizing on like basic things that you need, like matrix multiplication. So some of these things aren't going to change. Obviously, there will be things where, as you get into more esoteric math operations, you may not want to standardize on that. But I think there's some fairly well understood math operations that you probably do want to standardize on from an AI perspective.
Thanks. Other thoughts? Anybody thinking about AI?
Yeah, so Tenstorrent is actually focused on building the most efficient, scalable, high-performance AI compute platform, right? So your architecture will be able to scale from one single chip, right, to multiple, many thousand chips together. So the computation requirement for that is just similar to HPC. Like you look on we call TensXL, which is the basic computation element for the RISC-V. It's actually using the message passing semantic to communicate, right? So we have tightly coupled the RISC-V processor with our accelerator, and we have like SRAM, right, close by as a message passing buffer, right? So it's basically a tiny, element with a high performance, like, MPI kind of protocol going on there. So I don't see like we need to particularly design something for HPC because it's already working there. Right? So we are solving similar problem. It's a big matrix multiplication, sometimes sparse, sometimes dense, right? So we're solving similar problems. So if you solve that problem well, the AI problem well, then your product basically can be easily migrated by adding FP64 into it and become an HPC platform. That's what I strongly believe. So I honestly to say that I don't see that there's a particular thing we have to do. If we solve this domain well, can be easily mapped into HPC. And that's why I want to borrow the HPC knowledge to our product as well. Because if they can solve that problem well, they can solve AI problem well as well. Yeah.
I completely agree with that. I think we need to make sure we're pooling our resources and pooling our knowledge here so we benefit both sides.
Exactly.
So last week in the OCP Global Summit, someone was talking about Frontier and El Capitan, which are going to be the most powerful computers in the world. And he was saying, with AI coming in, we need to build more of these HPC systems. So it's basically AI is an HPC problem. So there is that side of the equation. There is the other side of the equation where right now, I don't know, in ISC this year, someone was, the keynote speaker was saying there is this 5 stages of AI acceptance in the scientific community. The first one is denial, the second one, and all of those 5 stages of, and then right now we are in the phase of acceptance, right? Like, or everyone is, like, we know that AI is going to help, is helping, actively helping solving scientific problems that otherwise would be intractable. So there is that side of the AI scientific endeavor as well. And I think there is also the fact that AI is causing, AI is pushing on the energy consumption of high performance computing. So, before AI, we were expecting energy consumption to become a problem at certain point in time where it was going to hit the limits of energy generation, of human energy, planetary energy generation. But now with AI, we see that this is going to happen very soon. So I think we have to be looking at AI as an HPC problem, and we really have to pay special attention to the power consumption issue that is going to, limit us, or is already limiting us.
Thank you. Moving on from AI workloads to some of the older workloads. I mean, Nick, we were speaking before. You've got a demo out in the demo theater of some AI workloads running on a Banana Pi. So you're saying a lot of scientific computing workloads are quite legacy. So for 20 years old or more, and people are just excited to get new hardware to run it on. It's not really about changing the workload. So, I mean, what do we need to do as an ecosystem to address, software from a standpoint of these workloads that are really quite old?
I mean, I think we need to learn from the likes of NVIDIA, because if you look at NVIDIA, they've invested huge amounts in the software ecosystem. And whenever I hear HPC people compare NVIDIA and AMD, it's very rarely on the hardware, it's always on the software, because they've got these libraries good to go, they've got the applications that they've optimized, and I think that's really, really important. I firmly believe, as I mentioned before, where we're going to start to see the adoption of RISC-V in HPC is in these accelerator cards. But it's a huge amount of effort to then take a Fortran code and port it over. And realistically, are people really going to do that when they're, just want to run their codes faster and reduced energy and whatnot? So I think as a community, we need to appreciate this and solve the programmability challenge and actually pool our resources across all these different accelerator cards potentially and say, look, we know what these basic building blocks are, things like BLAS, things like Fourier transforms. Let's actually develop these in a way that work across these different accelerators. Let's work on the compiler support so you can take your code and with minimal effort run them on these different accelerators and whatnot. That would be my thoughts on that one.
Thanks. Travis or Wei-Han, from a more commercial side, how do you see this? Or is
Nick already touched on some of the key things. It's you got to port these libraries over, which a lot of that's already happening. I don't know, I assume Kumar and Bernard are out there somewhere, so we're working with RISE. They have a vast expanse of software that they're optimizing on that. And so with this common ISA with RISC-V, you have a lot of companies coming together and cooperating for one architecture to get these things running.
Yeah, so I think what NVIDIA is winning today is not winning on their architecture, right? So they are winning on the completeness of their ecosystem. So they early investor on this, like for 13, 15 years, and then it's hard for the later entrant to actually catch up on this. But that's why they can charge an 85% margin product, right? So they go in for all this very expensive technology, persuade people to buy that technology and spend like tons of money on that. What people want to pay that money because the ecosystem is complete. So what Tenstorrent does is that we want to motivate people going for non-proprietary technology, right? and then also cheaper solution. And then so that in our strategy is that we're gonna have the price performance win like 5x to 10x compared to the NVIDIA product. Everybody know like NVIDIA GPUs pulls on solving some HPC problem, like if you have a strong, scaling problem, right? NVIDIA GPU do poorly, the utilization is very poor. I heard numbers something like 5% utilization on the hardware. So it's not a great architecture, but they are winning on the complete ecosystem. So that's why porting this, right, is very, very important. What we do is actually we open our hardware, we open our software ecosystem. You can download on GitHub and welcome people to contribute to this open ecosystem to catch up what NVIDIA has today. So ecosystem is super important. But I think the market need alternative solution, right? People cannot just pay 85% margin NVIDIA's pay. NVIDIA want to charge. I think we will win eventually.
Patricia, what are your thoughts on older software and how we?
I agree with everything that is being said here. I think the only thing that I would add is that software is different from when you're working in hardware. Software is something that is relatively more open, develops a little bit faster. So software would be something that could be a good candidate for AI to solve the problem we have for some.
Great. And speaking about open, how do you think the open nature of RISC-V changes the dynamics of HPC development in general?
I think it enables exploration, and it enables development, fast exploration. It enables reusability. So we have, in our group, we have a project where we are evaluating many different features that could or could not go into the future high-performance computer, and it's all based on RISC-V, and it's all based on a platform that has been developed and by others and has been contributed by the community. So I think it enables accelerated development. Is way more efficient to build on the shoulders of giants that having to develop everything from scratch.
You have a long history in HPC, Nick. What are your thoughts about how it changes things?
So not quite on the development, but I think it's very interesting that it can be used in lots of different ways. I was fascinated yesterday by the NVIDIA keynote, the fact that there's between 10 and 40 RISC-V cores in every chip that they ship. So I had a quick look on the top 500, the top 500 most powerful supercomputers. And out of the 10 on that, top 10, about 4 or 5 of them are NVIDIA. So I calculated in the top 10 most powerful supercomputers in the world, there's about 1 million RISC-V cores. Now, I'm being flippant, of course. You can't directly program them. But it really illustrates that already this is ubiquitous, and we rely on this technology because of the way it is. And using that same technology, we're now talking about using it in a different way. And we can do that because of the way it's been put together and the openness and all of this fits together. And I think that's just super exciting. All that effort that's been saved on all that pooling of resources. So yeah, that's my views on that.
Great. I guess from a commercial point of view, you're developing this stuff already, so you're well aware of the open nature of development. But selling that into customers, how do they view that? Do you think?
And the open development?
Yeah.
So let's talk about a couple of aspects. So one of them is the aspect of, we talked about the customization, right? So you're seeing more people doing that. And on top of that, what it is it's made it more accessible to have your own compute. So I think we also touched a little bit earlier on sovereign compute initiatives. So every country likes to have their own HPC/AI. They're kind of getting lumped together, although they're a little bit different, but there's some fundamentals in there together. But if you're building a national compute initiative, you don't want some company coming up and saying, no, actually you don't have a right to that architecture anymore, right? So you want to build that on something that's open, like RISC-V. And with that, you have, and especially when you have multiple companies you can work with to go and try to create these, you have something that you can customize. So you have that, again, we've touched on this before, but you've had this ability to do a sovereign compute initiative in a realistic manner, right? So many of these countries wouldn't have gone out before and said, I'm going to build my own compute supercomputer from scratch. Like, no, they're going to go buy off the part shelves. But what RISC-V's enabled these countries to do is, like, they can have a realistic sovereign compute initiative now. And that's one of the big changes I see going on. And you see this around the world.
Yeah. I really think the openness actually create a diversity and innovation. Right? So whatever the high performance computing you see today is from NVIDIA, AMD, Intel, right? Those companies are maybe on. But with this open standard, now you kind of all this option. Ventana can do it, Tenstorrent can do it, ABC company can do it. So this diversity and innovation will coming out with best design actually fitting the high performance computing better. So I'm betting that probability of the innovation will make RISC-V actually dominate, kind of architecture for the high performance computing. Yeah, so you're no longer controlled by Intel architecture, AMD architecture, NVIDIA architecture. So somewhere, someone may coming out with the greatest architecture in the world, or HPC.
Thank you. So we're nearly at time, but can I ask just sort of one final question of you all? Do you see any blocking factors for the RISC-V adoption in supercomputing applications? And if you had kind of a magic wand and you could change one thing to advance RISC-V and HPC, what would that be? Nick, what do you got?
I think the marketing, actually, not technical at all, but I think we need to be very clear on the why for HPC. And I think getting some case studies out, really having that message clear is crucial. Because if you've got $500 million, if you've got $1 billion to spend on a supercomputer, why would you not use x86 in NVIDIA? Now, there's a lot of good reasons, but we really need to tell the story behind that and convince these people. And I think that is a key part of the adoption that we need to cover.
Great. Travis, what do you reckon?
I would like to have my hardware today. I flog my engineers, hurry up, get it done, right? So here's the thing. A lot of people talk about the software, and software is a key portion of it. But the great thing I've seen with RISC-V is that I worked a lot on ARM, right, when we try to get into the data center. The software is actually way ahead of where it was at this stage. And so what we need right now is to just get the hardware out so that we can finish the final stages of the software right now. So it's actually exciting from that perspective. Obviously, there's more work to be done. Yeah. But the amount of readiness that comparatively for a new architecture, I think is quite amazing. And so yes, the sooner I can get my platforms out, the happier I'll be.
Great. Wei-Han, what do you think?
So I really want a really, really great CPU design team, right, implement the hardware with the best PPA possible you can. Because I think the RISC-V, like I say, semantic is not different from PowerPC, ARM and x86. The thing is about implementation, that high performance computing core, and then also everything around it is super, super important to win this war. Because you look on massive amount, like Fugaku had 160,000 core, 7 million core in there. So every power efficient actually count. To win this war, you actually need great implementation of this ISA. Currently, I see none of that, right? To win this war, to win this against x86, the RISC-V had to count the best implementation they can. And it's very, very difficult to do, right? Apple has been successful, right? But like you see Google doing it, NVIDIA even trying to do since 2004, right? They haven't successful yet. And Samsung tried to do, they closed it. Qualcomm is the second time they tried it. It's very, very difficult to do. So if you have Magic Wand, and then I hope there's a great implementation team, bring this ISA, bring the implementation to the next level.
Thank you. Patricia, what are your thoughts to sum up?
Yeah, so I would agree that accelerating the hardware development would be key. Right now, hardware is expensive, is slow, is overall expensive, I'm going to say. So if we could address that problem, would be great. And then I think the second problem I think is big for HPC right now is power consumption. We have to make sure that these cores are low power instead of, GPUs require 1,000 watts. So we need to make sure that a RISC-V core can deliver performance, but still stay in the low power consumption side. And that's something that we haven't seen before in high performance computing. We never cared, or not that much, but now we do have to care about that.
Thank you. Well, I think we've reached time at our panel. It's been a really great discussion. So thank you so much, everybody, for your opinions and your thoughts. It's been great. I just wanted to highlight, what Nick was saying about getting involved with RISC-V. So Nick, you're the chair, right, of the HPC working group. So get in touch with Nick if you want to be involved with that. And also we are, from a marketing side, we're starting, more activities on HPC market development. So we have a call where we're working out on messaging and things like a web page to get the word out about that. So if you or any of your team would like to be part of that, again, reach out to me or Nick. We can put you on the mailing list. But yeah, thank you very much for your time, and thank you for my panel.